Hi everyone. So we're on page 12 in the notebook and we're doing example 4. So comparing two averages or 2% is much more common than just comparing one sample to some claim. We often want to know if two groups differ from each other. For example, whether a treatment works better than a control, or if we're designing a study comparing two groups, we want to do power calculations to figure out what size sample we need in order to achieve a certain power. In the past, so far, we've just been looking at one sample z-test. So now we're going to look at two sample z-tests. All right. So we're going to use the same formula, the same power calculation as we did before. We have the distance right here. This is the distance in units. You can call it D in units, for example, D in actual units that we're measuring. And we're translating it into a distance in standard units in z-scores. So this z alpha plus z beta is the distance in z-scores, and then this is our conversion factor that translates between the two, the standard error. So this is the same exact formula we've been using, but now the standard error is going to change because we have variation, we have sampling variation coming from two sources if we have two groups that we're comparing. So we have to do a calculation here that's slightly different. We're going to be looking at the difference between two groups. The null is going to be that the two groups, whatever test statistic we're testing, is the same. There's no difference between them. And the alternative is going to say no. We're going to specify a certain effect size, right? So here's one group, a standard error from one group, and here's the standard error from the other group. And basically, the idea is that this the variance is sum, and the variance is the standard error squared. So we're just taking the square root of that. So it's the square root of the squares of the sum of the squares of each of their standard errors. We went over this in Stat 100. So we have two. So this is our usual standard error formula we've been using, the standard deviation over the square root of n, where it's the sample size of each group. And then if we have percents here, we'll just multiply it by average, by 100. Okay, so that is the idea. Now, in the examples we've been using, we have the same standard deviations in each group. And so we can just add these two together, and now we have two of the same standard errors, because we'll also, let's assume the same sample size, which is the optimal way to design the experiment, because if you assume the same, when you're designing an experiment, you can set it up any way you want. So if you set it up with equal sample sizes, that's going to be the optimal way to minimize the total number of people or subjects you'd need in your experiment. All right, so when both groups have the same sample size and the same standard deviation, this simplifies to the square root of 2, because it's just summing two things. So here you have two standard errors, so it's the square root of 2 times SD over the square root of n. Okay, and then, of course, if it's for percents, you have to change the decimal to a percent. All right, so now you understand that. If you want to look at the proof for that, you can look in the proofs in the back of this book. So now we suppose we want to test whether a new drug designed to help people quit smoking works better than the old one. So we plan to randomly assign half the subjects to the, half the subjects to the new drug and half to the old. Now, suppose under the old drug, half the people quit smoking, it works for half the people, but we think the new drug would work for at least 60% of the people, so 60% of the people would quit smoking. So so what we're going to do is set here, let's cross this out. This doesn't make sense. Sorry. So what we're going to do is we're going to set 10%. That difference, this is the difference that we're going to be detecting. The effect size is 10% as the effect size that we're trying to detect. At least 10%. Okay, and how big a sample size do we need in each group? And we're going to make the groups the same to detect that difference with a power of 80%. All right, so we're going to have 80% power here, and we're going to assume that alpha equals 5% as usual. All right, so let's set up our null and our alternative hypotheses. And the null is what? That the difference between the two drugs in the population is equal to 0. So the percent in the new drug, we'll call it the treatment, minus the percent in the control group, in the population as a whole, in the ideal population that we're sampling from, is equal to 0%. So there's no difference. It's the null is the hypothesis of no effect. All right, and then our alternative is, yes, there is a difference, that this treatment group works better than the old drug. So it's the new drug, the percent that get cured in that, or that quit smoking, minus the percent that quit smoking in the under the old condition, is like this is going to be greater. This was 60% minus the 50%. It's going to be greater or equal to 10%. Okay, so at least it's at least a 10% difference favoring which one? Favoring the new drug. So it's going to be a one-tailed test. So that's the idea. And then what we do is we just set up our usual distance. Here's our effect size, is 10% right here. And this is in actual units. We're measuring how much, 10% reduction. And we're going to say what is that equal to as a z-score, right? As a z-score. Well, that's going to be set by z alpha plus z beta, and it's a distance, so we're going to put these absolute value signs around it. Okay, and then in this case, they're basically always going to have the same standard error for the difference. So this is not a problem to distribute it out like that. Okay, now, so let's see what we're going to do. Well, we know this is 10%, right? We know, how do we get these? All right, so we want to get Z alpha and Z beta, and this is set by our, let's color them in here, by our, this one's Z alpha is the critical value of Z needed to get what? 5% in the tail. So because it's a one-tail test, so how we're going to figure out Z alpha, it's the usual way, right? Under the null. This is under the null. What we have is, because it's a one-sided test, we're going to have what in the tail here? 5%. So this 5% corresponds to this 5% in that direction, right? Which means, of course, 95% in this direction. So that's how we're dividing up this curve. And we see the Z that achieves that, Z equals 1.65, all right? If you use the table at the back of the book, you'd have to look up a middle area of 90%. So that's what goes here. And what goes for Z beta? Well, that's set by the power. So where's our power? Right here. Okay, and how do we figure that out? Well, we want to achieve a power. So this is under the alternative hypothesis. We want to set when we decide in one direction, these two are going to be overlapping. I'm just drawing it separately to show you what I mean here. When we draw that cutoff, we want it to be 80% of the time to make the right decision when the null is true. So when there really is at least, if the drug really does work at least 10% of the time, then we want to be able to detect that difference 80% of the time. So we want that to be 80%. And then making a type 2 error then is 20% right here. So that's the 20% going in this direction, right? And we're just trying to figure out the z-score that corresponds to having 20% in one tail like that, right? So that would mean, if you were looking at the back of the table, that would mean 40% on the tails together, and that would be 60% in the middle. And we saw, okay, so the way I drew it, it's going to be negative 0.85, right? But we're looking at distances. So that the absolute value of that is just 0.85. All right, so that's what we have there. And added together, that equals 2.5. And that's times the standard error for the difference. So now we know the standard error for the difference is what? The standard error for the difference is going to be 10% divided by 2.5, which is 4% difference. So now the idea is, how big an n do we need to achieve 4% standard error? Okay, so now we have the 10%, which is our effect size here, is equal to this. And so we just have to get the standard error for the difference. Now, as we said before, the standard error for the difference is given by this right here. So what do we have here? Let's see. Why don't we just divide both sides by, this is what, 1.65 plus 0.85, that's 2.5. So we get 10% divided by 2.5, which is equal to 4%. That's going to be equal to the standard error for the difference. So now we have the standard error for the difference, and we know that's this. So that's the square root of 2 times the standard deviation over the square root of n times 100. And that's a percent as well. All right, so basically, if we know the standard deviation, we can solve for n, and we are done. Now, what was the standard deviation? Let's look back up here, and we see the standard deviation refers to the standard deviation of the two samples. Now remember what we're doing here. We're doing this two-sample z-test. There's variation happening because both the old, this, what is this? The old drug and the new drug, let's say, have variation involved. So this one is, and what does the SDs refer to? They refer to the two different 50%, a 50-50 split and a 60-40 split. Well, remember how we said that the standard deviation of if there's a 50-50 split, the one SD would be equal to what? The square root of 0.5 times 0.5, and the other one would be equal to the square root of what? 0.4 times 0.6, 40%, 60% split, and those are so close to each other that we are going to just call them the same. And as far as we said, we have the same n, and that's the n actually that is the most efficient, that allows us the smallest to achieve the most power, to have an even number. So we're going to, that's how we're designing the experiment, so that's what we did. So n is the size of each sample. And remember that this formula is applicable here because there's certainly independence between the two samples. How well, whether somebody quit smoking with the old drug has no effect on whether somebody else is quitting smoking under the new drug, right? Okay, so quitting or not under the new drug. So I think we're good. So this, we say, we're just going to, since these are so close, these are this is equal to 0.5 and this is approximately equal to 0.5. That's the SD we're going to use. So we're good there. So we'll say the square root of 2 times 0.5 times 100%. And now we just have to solve for square root of n. Okay, so we'll say what? The square root of n is equal to the square root of 2 times 0.5 times 100. That's 50 over 4. So that's 12.5. So now that means when we square n, square both sides, we get n. We get equals 2 times, we said that's 12.5 squared. Right? Now, what did I do? Oh, there's a percent there. Yeah, I was saying n is not a percent, it's a number. So that's why these cancel and we get a number. All right, so what is that? That is equal to 312.5. And now that is a sample of, what is that? N is how big a sample we need in each group. Now we're going to round to the nearest whole integer. We're going to round up. So this will round to 313. And that is the number for each group. So now remember, if you were actually, our whole sample size has to be pretty big. It has to be 626. So we should write that down. So that's 313 in each group, which is what they asked for. But that means, which means that we have to do an experiment with twice that, because there's two groups, with 313 times 2 equal to 626 people. Okay? And this problem is very similar to what's your homework problem, homework 3, problem number 1 on the flu vaccine. Okay, so I think that's it. I'll just say goodbye.